Hello, my name is Peter Heringer, and today I'm going to present a poster on connecting FHIR patient data with the pangenome graphs using the semantic web. So the motivation behind our work is that the Human Pangenome Research Consortium just created the first draft human pangenome, and this gives us the possibility in the future to have pangenome graphs personalized for patients. So personalized medicine would benefit by that. Currently, however, there's no way to connect patient data efficiently and on large scale with these pangenome graphs, but that would allow us to do new analysis techniques and also significantly shorten the work required for older techniques such as genome-wide association studies. What are pangenome graphs? So you can see a pangenome graph in this picture. Basically, they represent the genomic diversity of a group of individuals, most often a species or a clade. And we have these nodes that are labeled with sequences and genomes that are represented as paths through the graph. And edges connect nodes that are also connected by a path. The second technique that we use for our work is the semantic web, which is a collection of technologies that have the purpose of making data machine readable, particularly on the World Wide Web. Most often the data itself is stored in the resource descriptor framework, which encodes information in triples such as this that have a subject, a predicate, and an object. This data can then be queried using Sparkle, which is a query language that looks very similar to SQL queries. And the patient data that we used was encoded using the FHIR format, which is a format for both storing and exchanging patient-related data. And this format groups data into resources, with possible resources being patients, observations, or treatments. And the storage itself can be done in a variety of formats, in this case the JSON, XML, or RDF files. We chose for our work RDF files, so to make the semantic web to the work. To combine the data, we created a new tool called Oxical, which is highlighted in green. And this basically takes an input query, a single federated Sparkle query, and gets some patient data from another endpoint, another Sparkle endpoint that has access to this FHIR data, creates subqueries from that that are sent to the intermediate backend. This intermediate backend was written by us and is entirely new code, and also gets the data from the pangenome graphs using RS handle graph. It then sends back triples to the Sparkle engine, and this Sparkle engine then combines the patient data with these triples into an output of a tabular format, which can then be used, for example, in a sequence tube map visualization as shown here in this picture. So how does Oxical represent pangenome graphs to the user? Basically, the pangenome graphs are represented using RDF with the VG and Foldo ontologies. And in these ontologies, nodes, paths, and steps are subjects of RDF statements with their properties listed in each statement. Edges are no specific subjects. Instead, they are represented as links between nodes, with nodes in this case being subjects and objects. How can the user then join this pangenome representation with patient data? For this, the user can use federated queries which gets some part of their data using a service statement from a FHIR store. Like in this query, we ask the FHIR data store at this address for some patient-related data and combine this with some pangenome-related data. This simple query has the purpose of getting all the nodes that are visited by paths, which correspond to patients that in turn are linked to the condition osteoporosis. And so we can look at this collection of nodes. This query is shortened a bit for legibility, but in practice it is not much longer. So what are our current limitations? Currently we are still missing parallelization for Oxical. There are also some data types missing, which would reduce the amount of memory that Oxical uses. And there can also be a few more shortcuts in the way Oxical deals with common queries, all of which would make Oxical faster and reduce its memory footprint. This has the purpose of increasing the number of haplotypes that Oxical can handle, because currently Oxical can work with small graphs like the draft human pangenome graph released by FHIR, but not with bigger graphs like they plan to release in the future. This was it from our side. Thank you very much for your attention.